South of Greenland and Iceland, there is a patch of open ocean roughly the size of Mexico that has been doing something no other stretch of water on this planet is doing. While every other ocean basin has been warming for decades, this one has been cooling. Quietly, stubbornly, for more than a century. Scientists call it the cold blob, and the latest measurements say it has lost close to nearly 1 degree Celsius, or about 1.8 degrees Fahrenheit, since 1900, even as the planet around it heated up. For years, nobody could agree on why. Some blamed the wind, some blamed the clouds. And then a team of researchers went looking at data stretching back over a century. And what they found didn't just answer the mystery of one strange patch of sea. It pointed straight at something far bigger, something moving beneath the surface of the entire Atlantic Ocean. A great current system, the one that keeps Europe from freezing and helps steer weather on both sides of the ocean, is slowing down. And the newest science says it may be doing so faster and closer to a dangerous threshold than almost anyone predicted even 2 years ago. I'm going to show you exactly what that current is, what the buoys strung across the Atlantic have been quietly recording since 2004. Why one of the most cited scientists in this field just called the evidence a serious concern for society and policy. And what happens to London, to New York, to the entire rhythm of the seasons if this thing actually stops. Including the part almost nobody is talking about. The country that watches this current most closely just started pulling its own sensors out of the water. Before we go further, hit subscribe, because this is not a story that ends with this video. The Atlantic is being measured in real time, right now, by scientists who are watching for the exact signals we're about to walk through together. And when the next reading comes in, whether it's reassuring or alarming, we're going to be here to break it down, without the hype and without the hand-waving. So subscribe, because the next chapter of this story is already accumulating in the data, one buoy reading at a time, and we intend to be ready for it. And while you're here, tell me in the comments where in the world you're watching this from. Some of you are on the coast this current touches directly, in Bergen or Boston or Belfast, and some of you are nowhere near an ocean at all. I want to know. And here's my second question for you. Had you heard of the AMOC before this video? Or is this the first time this current has ever crossed your radar? Let's find out together. There's a reason this story starts with an image rather than an equation. And the image is a belt. Not a metaphorical belt in the loose sense. An actual, specific diagram drawn in 1987 by a geochemist at Columbia University named Wallace Broecker, who is trying to explain to the rest of us why the ocean isn't just a big bathtub of salt water sitting still. Broecker published his famous Great Ocean Conveyor Belt diagram in 1987 to illustrate how interconnected ocean circulation really is. It became one of the most reproduced images in climate science, and for good reason. It took something almost impossible to picture, a system spanning every major ocean basin, and turned it into a single, sweeping loop that a room full of non-scientists could actually follow with their eyes. Here's the mechanism underneath that image, and I promise it's simpler than it sounds. The conveyor belt runs on density differences in seawater, controlled by two variables, temperature and salinity, a process scientists call thermohaline circulation, from the Greek words for heat and salt. Warm water near the surface travels north from the tropics, carried partly by wind and partly by the shape of the ocean basin itself. As it moves north, up along the eastern coast of North America and across toward Europe, it does two things. It cools, and, because seawater constantly evaporates, leaving salt behind, it also becomes saltier and saltier along the way. Cold and salty water is heavy water. Think of it like a suitcase you keep adding weight to as you carry it across a room. Eventually, up near Greenland, Iceland, and the Norwegian Sea, that water becomes so dense it can't stay on the surface anymore. It sinks. straight down, thousands of meters, in one of the only places on the entire planet where this happens at this scale. Once it sinks, it turns around and creeps back south along the ocean floor, eventually resurfacing, mostly thousands of years later in the Southern Ocean and the Pacific, to begin the whole cycle again. That sinking point is the engine room. It's the part of the machine that makes the rest of the belt move, in the same way a water wheel at the bottom of a mill makes the whole mechanism turn upstream. Break the water wheel, and it doesn't matter how much water is flowing above it, the system stops pulling. Now, this is where people get the terminology tangled, and it matters enough to slow down for. The Gulf Stream is not the same thing as the AMOC, even though the two get used interchangeably in headlines constantly. The Gulf Stream is one of the fastest ocean currents on the planet, reaching peak velocities of 2 to 2.5 meters per second. That's roughly 4 to 5.5 miles an hour, about the pace of a brisk walk, which sounds unimpressive until you remember this is an entire river of ocean moving at that speed, not a stream of water in a pipe. The Gulf Stream is mostly wind-driven, and it's a near-surface phenomenon hugging the coast of the United States before bending out across the Atlantic. The AMOC, the Atlantic Meridional Overturning Circulation, is the larger, deeper, slower system that the Gulf Stream feeds into and forms one component of. It's driven not primarily by wind, but by that sinking, density-driven engine up near Greenland. You can lose the Gulf Stream's shape without losing the AMOC's overturning, and you can weaken the AMOC's overturning while the Gulf Stream itself, closer to the surface, keeps mostly humming along. They rise and fall together over the long run, but they are not one and the same machine. And every time you see a headline about the Gulf Stream shutting down, what the scientists are usually actually worried about is the AMOC underneath it. And it is worth pausing on just how much water we are talking about. Oceanographers measure the strength of the AMOC in a unit called the sverdrup, named after a Norwegian oceanographer, where one sverdrup equals 1 million cubic meters of water moving past a point every second. The flow rate of the AMOC averages about 18 sverdrups per second, though it can vary between 12 and 25 sverdrups. To put that in a shape your mind can actually hold, the strength of the AMOC is about 18 million cubic meters of water per second. By comparison, the Amazon River, one of the largest rivers in the world, moves about 200,000 cubic meters per second. That means the AMOC, at its ordinary healthy strength, is moving something on the order of 90 Amazon rivers, all at once, day and night, winter and summer, in a loop that spans the entire Atlantic basin. That is the scale of the machine we are discussing here. That is what a 1 or 2 sverdrup change actually represents when it shows up in a spreadsheet. It's not a rounding error. It's rivers. And why should you, sitting wherever you're sitting right now, actually care about a deep ocean current thousands of feet down in the middle of the Atlantic? Because of heat. The AMOC carries up to 25% of the total heat transported toward the northern hemisphere, and almost none of that heat is evenly distributed. It's concentrated exactly where it does the most good for the people living around the North Atlantic Rim. Here's the comparison that should genuinely stop you. London, England, sits at 51 degrees north latitude. Quebec City, in Canada, sits at 47 degrees north, several degrees closer to the equator than London. By the raw geometry of the planet, Quebec should be the milder of the two cities. It is not close. London, England, and Quebec City, Canada, sit at roughly the same latitude, but have vastly different climates. Quebec City had 99 freezing days in an average year, while London only experienced 3 freezing days in an average year, despite being slightly further north. 99 days below freezing against 3. That gap is not an accident of geography. It is the AMOC, quietly doing its job, delivering tropical heat across an ocean and handing it to a continent that on paper has no right to be that mild. This is the part of the story where the ancient history stops being trivia and starts being a warning label. We know this current has stopped before. Not gradually slowed, but actually shut down abruptly in the recent geological past. Roughly 12,800 years ago, at the tail end of the last ice age, as the planet was warming and glaciers were retreating, something interrupted the thaw with startling violence. It's called the Younger Dryas, and the numbers from it are almost hard to believe. Annual air temperatures decreased by roughly 3 degrees Celsius over North America, 2 to 6 degrees Celsius in Europe, and up to 10 degrees Celsius in Greenland, in a matter of decades. And in Greenland itself, the cooling was particularly rapid, taking place over just 3 years or less. 3 years. Not 3 decades, 3 years, for a swing of nearly 18 degrees Fahrenheit. The leading explanation, built from ice cores, ocean sediment, and decades of modeling, is that a massive pulse of glacial meltwater, fresh water, lighter than salty ocean water, poured into the North Atlantic and effectively jammed the engine room. It diluted the salty water that was supposed to sink, so it stopped sinking. So the whole belt stalled, so the heat stopped arriving. Europe, mid-thaw, was shoved back toward the deep freeze for over 1,000 years before the system found its footing again. Here's why that story isn't just paleoclimate trivia. Right now, in the exact region where that ancient engine room sits, we are pouring in fresh water again. Not from a catastrophic ice dam bursting all at once, but from something slower and in some ways stranger. The steady, accelerating melt of the Greenland ice sheet, plus a warming atmosphere that is making the whole North Atlantic less salty at the surface than it used to be. Nobody serious is predicting a 3-year Younger Dryas-style slam this century, but the mechanism, fresh water weakening the sinking weakening the pull weakening the whole belt, is exactly the same physics, just turned down to a much slower dial. And the question that has consumed oceanographers for the last 2 decades is whether slower is actually the right word anymore, or whether the dial has started turning faster than anyone's model accounted for. That question is exactly why, in the spring of 2004, a small international team dropped a string of instruments into the Atlantic Ocean and, for the first time in human history, gave us something we had never had before: eyes on the AMOC in real time. Before that spring, understanding what this current was doing meant piecing together scraps. Research ships would sail out, drop instruments, take a snapshot, and sail home, and then wait years, sometimes a full decade, before another ship could do it again. It's a little like trying to understand a person's heartbeat from a single stethoscope check once every few years. You might catch that the heart is beating. You have almost no chance of catching an arrhythmia. Until 2004, when researchers deployed and began monitoring a series of moored current meters and temperature sensors on the Atlantic's 26.5-degree north parallel, stretching from the Bahamas to Morocco, the understanding of the AMOC was based on sparse, ship-based observations. This became known as the Rapid Mocha Array, and it changed everything. Because for the first time, the ocean could talk continuously, instead of only when someone happened to be listening. There's a detail about how those instruments were built that I love, because it tells you everything about how unglamorous real oceanography actually is. These are not sleek, futuristic probes. Many of the moorings were designed by members of the Rosenstiel School's Ocean Technology Group, who anchored the high-tech buoys with old railroad wheels somewhere at the bottom of the Atlantic Ocean, in water so deep it would crush an unprotected human body in an instant. Some of the most sophisticated climate sensors on the planet are being held in place by literal train wheels. It's a strange, almost funny detail, until you realize that this scrappy, improvised setup has become one of the most important scientific instruments of the 21st century. For the first several years, the array mostly told a reassuring story. Yes, the current wobbled. Yes, there were seasons, but nothing screamed emergency. Then came the winter of 2009 into 2010, and the buoys recorded something nobody expected. From autumn 2009 to spring 2010, the observations revealed a substantial weakening of the AMOC, and a second weakening event occurred in late 2010. This wasn't a subtle wiggle in the data. A 2015 Nature study pointed to a 30% downturn of the AMOC over 2009 to 2010 as one of the drivers behind an honestly startling side effect: an unprecedented 128-millimeter jump in sea level north of New York City over that same 2-year period. 128 millimeters is about 5 inches. Sea level jumping 5 inches in 2 years along a stretch of American coastline, apparently connected to a current weakening thousands of miles away in the middle of the Atlantic. That's the data not just being unusual, but reaching out and touching real coastlines in ways nobody had fully modeled. And it got stranger. These weakening events coincided with record-low states of the North Atlantic Oscillation and cold winter conditions over Europe. The same winters that had European commentators wondering, only half-jokingly, whether the Gulf Stream itself was failing, right as headlines about global warming dominated the news. Anomalies of this magnitude were not seen in state-of-the-art climate models, calling into question the reliability of those models to serve as guides for future behavior of the AMOC. Read that sentence again, because it's the whole tension of this entire field in one line. The best computer simulations in the world, built by some of the smartest oceanographers alive, did not predict a swing this large. The ocean did something the models said it basically couldn't do. And the only reason anyone caught it at all was that a handful of railroad wheel-anchored buoys happened to be sitting exactly where the drama was unfolding. An instrument built to confirm a slow, boring, decades-long decline instead caught the ocean breaking its own rulebook within a single winter. And the response from the scientific community wasn't relief that it recovered afterward. It was the opposite. It was the uncomfortable realization that our models of how this current behaves might simply be missing something. The value of the array was likely to increase further as the length of the record increased, and as a more robust picture of the year-to-year variations developed, and perhaps as further surprises emerged. That line, written by the very scientists running the array, reads almost like a prophecy now. Because more surprises did emerge, and they kept emerging, decade after decade, each one sharpening the picture. The rapid array kept running. A sister array called OSNAP went in further north, in the subpolar Atlantic, to watch the engine room itself rather than just the traffic passing by at 26 degrees north. And by the 2020s, a completely separate observing effort, this one from the University of Miami's Rosenstiel School, using 4 different moorings strung along the western boundary of the North Atlantic, delivered a result that landed like a second confirmation nobody had been quite ready for. Researchers analyzed real-world data from 4 moorings along the western boundary of the North Atlantic Ocean, which have measured water temperature, salinity, and the velocity of ocean currents since 2004, and found the AMOC has been weakening at 4 different latitudes over the past 2 decades. 4 separate locations, all telling the same story independently. The fact that weakening was observed at all 4 locations is significant, said Shane Ellipott, the physical oceanographer who helped lead the analysis, because it meant this wasn't one sensor drifting out of calibration or one regional quirk. It was a signal running the length of the current's western edge. This is where the chapter turns into something that should genuinely unsettle you. Not because of what the ocean is doing, but because of what is happening to the instruments watching it. At the exact moment the signal has gotten loud enough to draw 4 independent moorings into agreement. At the exact moment researchers are calling this some of the strongest direct observational evidence so far of a weakening current, the United States has begun pulling sensors out of the water. In 2025, the Trump administration moved to dismantle a monitoring system that provides critical data on the world's oceans, sparking alarm among scientists. And among the arrays affected are autonomous buoys and gliders that track ocean health in a region that matters enormously for this exact story. The National Science Foundation announced the removal of all in-water infrastructure belonging to the Ocean Observatories Initiative at sites including the waters between Greenland and Iceland, the Irminger Sea, one of the very engine rooms of the overturning circulation we've just spent the last several minutes describing. Data gathered at the observation station in the Irminger Sea has been key to understanding the AMOC, which scientists fear is gradually weakening due to planetary heating and could ultimately collapse. Stefan Rahmstorff, a name you're going to hear again and again in this story, one of the most cited oceans and climate physicists alive, currently at Potsdam University, put it plainly. The AMOC is a system of ocean currents that delivers warmth to northern Europe and shapes climate globally. And scientists are increasingly concerned it may be nearing a tipping point. He added, of the moment we're living through right now, ongoing monitoring of the ocean is critical, especially now. Concern in the oceanography community about major ocean current changes ahead is large. Think about what that means for a second. Imagine a hospital patient hooked up to a heart monitor, and the readings on that monitor have just started showing an irregular rhythm nobody fully understands. And at that exact moment, someone walks into the room and unplugs half the sensors. That's not a metaphor I'm reaching for lightly. It is, almost beat for beat, the actual situation unfolding in the Irminger Sea right now, while you're watching this. So that's where the story stood, going into the most recent round of research. A conveyor belt the size of a planet, discovered to wobble far more violently than any model expected, now watched by a shrinking set of eyes at the precise moment its signal is getting harder to ignore. And that cold, stubborn patch of ocean we started with, the one south of Greenland that's been chilling for over 100 years while the rest of the planet cooks, turns out to be the clearest fingerprint yet of exactly what those buoys have been whispering about since 2009. What that fingerprint actually reveals, and just how much colder that patch has been getting compared to what the models expected, is where this story gets its sharpest turn yet. There's a patch of the North Atlantic where the ocean is telling a story the rest of the planet refuses to tell. And it's worth standing there a moment, because the shape of that story is the whole shape of this crisis in miniature. Call it what the papers call it, the cold blob that shouldn't exist. Picture the North Atlantic as a kitchen radiator, the kind with hot water piped in from a boiler somewhere out of sight, warming a room from one end to the other. For 100 years, the boiler for planet Earth has been running hotter and hotter. Greenhouse gases trapping more energy, oceans worldwide absorbing more than 90% of that extra heat. Sea surface temperatures climbing almost everywhere you check a thermometer. Almost everywhere. There is one patch of radiator, south of Greenland and Iceland, roughly the size of Mexico, that has stayed cold. Not just failed to warm as fast as its neighbors, actually cooled by close to 1 degree Celsius, nearly 2 degrees Fahrenheit, since the year 1900, while the global ocean average rose by roughly the same amount in the opposite direction. Stand at that patch of ocean and look at a satellite temperature map, and it looks like a hole punched clean through the middle of a heating planet. Sailors and fishermen noticed something was off in that region for years before scientists put a name to it. The water just didn't feel right for the season. Here's the physical reason a cold spot like this can exist in a warming world, and it comes back to the belt we spent the last chapter describing. That patch of ocean sits almost directly above the engine room, the exact stretch of sea where warm, salty water is supposed to get heavy enough to sink and drive the whole overturning circulation. When the AMOC runs at full strength, it's constantly ferrying warm water up from the tropics and dumping it right there, like a delivery truck making the same drop every day without fail. Slow that delivery truck down, and the drop-off point stops getting resupplied with heat at the same rate. The water sitting there doesn't have to gain any cold from anywhere else. It simply stops getting as much warmth as it used to, while the rest of the ocean keeps baking in greenhouse heat. A cooling AMOC doesn't need an ice age to make a cold spot. It just needs to fail at its one job, delivering warmth to that exact address, more and more each year. Stefan Rahmstorf and his colleagues were among the first to connect this cold patch directly to a weakening circulation, publishing analysis showing that a subpolar Atlantic cooling trend was consistent with, and largely explained by, a slowing overturning current, rather than any local, temporary weather quirk. Other researchers, including a team led by Florian Sevalek and Sybren Dreifhout, ran forward simulations years earlier that had actually predicted a cooling patch like this one would appear south of Greenland as an early fingerprint of AMOC decline, well before satellite records confirmed it was really there. That's worth sitting with for a second. A computer model predicted the exact shape and location of an anomaly years in advance of it showing up in real ocean data. When a prediction like that comes true, in the exact place and in roughly the expected size, that's not a coincidence you can wave away. That's a fingerprint match. Pay attention to this next part, because it should genuinely give you pause. If the cold blob were simply a fluke of natural variability, a decade or two of unlucky winds, a passing quirk of atmospheric pressure, you'd expect it to come and go, appearing for a few years, vanishing, reappearing somewhere slightly different. It hasn't done that. It has persisted on and off for over a century, deepening at exactly the moments the rapid buoys and the AMOC array were independently recording weakness in the overturning current itself. Two completely different lines of evidence, one from satellites reading sea surface temperature from space, one from railroad wheel-anchored instruments sitting on the ocean floor, arriving at the same conclusion without either one having been designed to check the other's work. In science, that kind of unplanned agreement is about as close to a smoking gun as you get. So the cold blob isn't just an anomaly anymore. It's a warning label, written across an area of ocean bigger than most countries, visible from space, readable by anyone who bothers to look at a temperature map instead of a headline. And it forces the next question, the one that took the field from curiosity to something closer to alarm. If the current really is behind this, how much has it actually slowed? Because for the longest time, the honest answer coming out of climate models was, probably not by much. Not yet. Not for decades. The observations were about to tell a very different story. It starts with a study published in Nature in 2018 by Levka Caesar, Rahmstorf, and colleagues using ocean temperature patterns as a long-range proxy for circulation strength, because direct measurements only go back to 2004, and this question needed a longer memory than that. Their conclusion? The AMOC has weakened by around 15% since the middle of the 20th century, reaching its weakest state in more than 1,000 years. A separate reconstruction the same year, led by David Thornalley using deep-sea sediment cores, tiny shelled organisms that lock ocean temperature and circulation signals into their shells over centuries, pushed that record even further back and reached almost the same unsettling conclusion from a completely different method. The current circulation strength was unprecedented in at least the past 1,600 years. 15% sounds almost survivable, doesn't it? A car engine running at 85% power still gets you to work. But ocean circulation doesn't behave like a car engine coasting gently downward. It behaves more like a bank account that looks perfectly healthy right up until an automatic payment bounces. Because the danger in this system was never about the average state. It was about the shape of the decline curve as you approach a threshold. And when researchers went back to compare what the observation-based reconstructions were showing against what the best coupled climate models, the same models used to write IPCC reports, had projected for this exact period, the gap was uncomfortably wide. The real ocean was weakening faster and further than the simulations run for policymakers had led anyone to expect. Some analyses of the discrepancy between the observed decline and the modeled decline put the shortfall at close to a quarter of the current's projected strength for this point in the century. Models built on a century of physics, still catching up to what a strip of ocean floor sensors and ancient shells had already recorded. Let me put 25% into something you can actually feel in your body. Go back to the number from the last chapter. 18 million cubic meters of water moving past a single line in the ocean every second. Something like 90 Amazon rivers running side by side. Shave a quarter off that, and you have removed the equivalent of more than 20 Amazon rivers worth of warm water that used to be delivered north every single second and isn't arriving anymore. That's not a statistical footnote. That's the heating system for an entire ocean basin, running with a fifth of its radiators disconnected, and nobody in the building agreeing yet on exactly when the cold started creeping into the walls. And the timing of that shortfall matters more than the number itself. Every projection about what happens to European winters, to American coastlines, to fisheries and storm tracks and growing seasons, has been built on model runs that we now have good reason to believe were too conservative. If the models underestimated the slowdown that's already happened, what confidence should we have in their estimates of how much further and how much faster this goes from here? That question. Not the 15%, not the 25%, but the honest admission that the observed world has been outrunning the simulated one, is what pushed this from an academic curiosity into something oceanographers now discuss with real unease in their voices. Which brings us to the question every single person in this field gets asked, and the one almost none of them will answer with a straight number. I want to be honest with you here about why that's true, rather than pretending there's a hidden number scientists just haven't announced yet. The AMOC belongs to a family of systems physicists called bistable, meaning it doesn't have to change gradually and reversibly the way a dimmer switch does. It can behave more like a light switch with a spring in it, holding stubbornly in the on position under increasing pressure, then flipping abruptly to off once that pressure crosses a hidden threshold, and, this is the frightening part, refusing to flip back on again just because the pressure eases afterward. Oceanographers have understood this mathematically since 1961, when Henry Stommel published a simple model showing that ocean circulation could have two stable states, separated by exactly this kind of cliff edge, decades before satellites or subsea buoys existed to check whether the real Atlantic actually behaved that way. What the last 20 years of observation have done is take Stommel's abstract math and start filling it in with real measured numbers from a real weakening current. The trouble is that a system like this gives you almost no warning as you approach the edge, and then very little time once you're over it. Picture walking across a frozen lake in thick fog. For a long stretch, every step feels exactly like the last one. The ice doesn't get visibly thinner as you approach the weak patch. It doesn't creak progressively louder with each stride to give you a countdown. It holds, and holds, and holds, until the one step where it simply doesn't, and by then you're not walking anymore, you're falling. And the transition from solid to broken took less time than it takes to finish this sentence. That is the shape of a tipping point, And it's precisely what makes this so much harder to forecast than a hurricane or a heat wave. A hurricane gives you a track, a pressure reading, hours or days of lead time. A tipping point, almost by mathematical definition, gives you fog, right up until it doesn't. That hasn't stopped scientists from trying to find the cracks in the ice before they widen. In 2021, Niklas Boers at the Potsdam Institute published an analysis in Nature Climate Change using 8 independent indicators, sea surface temperature and salinity patterns across the Atlantic, looking for the kind of statistical fingerprints that physicists associate with a system losing its stability. Reduced resilience, slower recovery from small disturbances, the sort of sluggish wobble an engine makes right before it stalls, rather than while it's running fine. His conclusion, stated with real scientific caution, was that the AMOC may have already lost stability over the course of the last century, an effect that should be reflected in critical slowing down, and that this decline may be associated with an almost complete loss of stability. Not the AMOC will collapse next Tuesday. Loss of stability. The ice getting quietly, invisibly thinner underfoot, long before anyone can point to the exact spot where it gives way. Then, in 2023, a very different kind of estimate landed, and it hit far harder than an academic paper usually does, because it did something Boers had carefully avoided. It put an actual window on the calendar. Susanne Ditlevsen and Peter Ditlevsen, using centuries of sea surface temperature data as an early warning proxy, published a statistical extrapolation suggesting the AMOC could collapse somewhere between 2025 and 2095, with a central estimate landing around 2057. A date. Not a vague, later this century, but a specific year, inside a specific decade, inside most of our own lifetimes or our children's. It made headlines everywhere, and it also triggered one of the sharpest scientific rebuttals this field has seen in years. Dozens of oceanographers, including several who run the very observation networks we've been walking through, publicly pushed back, arguing that using sea surface temperature alone as a stand-in for the deep overturning current is a shaky substitute, that the statistical method assumes a kind of behavior the real ocean may not actually follow, and that a single number like 2057 risks giving false precision to something that remains, in the words of the IPCC's own 6th assessment report, a matter of low confidence beyond this century, with high confidence only that an abrupt collapse is very unlikely before 2100. So where does that leave us, honestly? Not with a date, with a direction, and a widening set of warning signs, and a community of serious scientists who disagree, sometimes sharply, about how close the edge actually is, while agreeing almost unanimously on one thing: the risk is no longer small enough to dismiss. That kind of disagreement isn't a failure of science. It's what science sounds like when it's staring at something genuinely unprecedented, standing in the fog, refusing to pretend it can see further than it actually can. And that unease is exactly why this chapter isn't really about a date at all. It's about the fact that nobody, not Ramstorff, not the Ditlevsens, not the IPCC's own authors, will tell you the ice is definitely solid all the way across. Now hold that fog in your mind, because it's about to meet the cruelest twist this whole story has to offer. The one that explains why a warming planet can, in specific places, at specific moments, feel like the opposite. Start with the seesaw. On one end sits the global average temperature, climbing steadily, driven by greenhouse gases trapping heat everywhere at once. The ocean, the atmosphere, the ice sheets, all of it rising together, slowly, relentlessly, decade over decade. On the other end sits the specific local temperature over northwestern Europe and the waters around the British Isles, which depends heavily on one thing the global average doesn't care about at all: how much heat the AMOC is physically delivering to that address right now, this winter. Turn up the global thermostat, and the seesaw's midpoint should rise too. But if the AMOC is simultaneously weakening, the delivery truck reaching that specific stop is bringing less warmth, even as the warehouse it's driving from gets hotter and hotter. You can have both things true in the same decade. The planet as a whole warming faster than at any point in recorded history, and a specific patch of ocean, and the coastline downwind of it, getting colder shipments of heat than it used to receive. That's not a contradiction in the data. It's two different mechanisms, operating at two different scales, and the mistake is assuming they have to move in the same direction just because they share a map. Here's where it gets even stranger. And this is the detail that made climate scientists sit up. A slowing AMOC doesn't just cool one patch of ocean. It appears to change the shape of the jet stream, the fast-moving river of air several miles up that steers Europe's weather from west to east. Michael Mann and other researchers have proposed a mechanism where the cold blob, by altering the north-south temperature gradient across the North Atlantic, encourages the jet stream to buckle into a wavier, more meandering path instead of its usual straighter track. The atmospheric equivalent of a river switching from a clean channel to a series of slow, looping bends. A wavier jet stream tends to get stuck, parking the same weather pattern over the same region for days or weeks at a time instead of cycling it through. And which weather gets parked where depends entirely on which side of the wave a country happens to sit on. Sit on the trough side and you can get locked in cold spells. The kind of prolonged chill that had Britain shivering through the beast from the east cold snap in early 2018. Arriving on the tail of one of those recorded AMOC weakening pulses we discussed earlier. Sit on the ridge side, just a few hundred miles away over continental Western Europe, and that same buckled jet stream can just as easily trap a dome of heat in place, contributing to the kind of punishing, record-setting heat waves that have scorched France and Germany in recent summers. Same mechanism, same weakening current, two opposite-looking symptoms, depending on which side of the wave your city happens to fall. That's the paradox in full, and it's worth saying plainly because it's the exact opposite of the doomed cartoon version of this story that occasionally shows up in disaster movies. A weakening AMOC doesn't necessarily mean Europe simply, uniformly, predictably freezes. It means Europe's weather gets less patient, more locked in, more prone to sitting still in whatever extreme it lands in, cold or hot, for far longer than it used to. Because the very system that once smoothed and moderated the atmosphere above the North Atlantic is losing some of its grip on the dial. Ramstorff has described the risk in blunter terms still. Not just harsher winters, but a weather system across the whole North Atlantic sector becoming, in his words, more chaotic and unpredictable. Extreme heat, extreme cold, and violent swings between them, arriving with less warning and less regularity than the seasons Europeans have built their agriculture, their infrastructure, and their expectations around for centuries. And none of this is hypothetical anymore, waiting patiently in a future decade for us to arrive at it. Right now, this winter, as you're watching this, the cold blob sits south of Greenland, exactly where the satellites have tracked it for years, still measurably colder than the ocean around it. Still sitting almost precisely above the stretch of seafloor where the rapid and OSNAP arrays have logged their strangest, sharpest weakening events. The pattern isn't a forecast anymore. It's a live reading, updating in real time, from an ocean that has been trying to tell us something since at least the winter of 2009, in language we've only recently learned to translate. Which leaves one very large, very obvious question hanging over everything we've covered so far. A question this entire chapter has quietly sidestepped by staying fixed on one side of the ocean. Because if a weakening current can bend the jet stream, freeze one coastline and bake another, all from a patch of water south of Greenland, then somewhere on the far side of that same Atlantic, along a coastline where over 100 million people live, work, and build their homes within sight of the tide line, that same slowing current has to be leaving its fingerprints too. And it has been. Since long before most of those people ever heard the word AMOC at all. There is a stretch of the American coastline, running roughly from Cape Hatteras in North Carolina up through New York Harbor and on into the Gulf of Maine, that oceanographers have taken to calling, without much affection, the hot spot. Not because it's warm, because it's sinking. Or rather, because the sea around it is rising far faster than it has almost anywhere else on the planet. A landmark study, led by Asbury Salinger of the United States Geological Survey, published in 2012, found that sea levels along this stretch were rising at rates 3 to 4 times the global average. And some individual tide gauges, Norfolk, Virginia among the worst of them, have logged even sharper increases still. Norfolk has become something of a case study in slow-motion crisis. Naval facilities flooding on ordinary high tides that would have stayed dry 30 years ago. Streets that now flood not during hurricanes, but during what residents have started calling sunny day floods. Water rising out of storm drains on a calm afternoon with not a cloud in the sky. For years, the standard explanation was simple and mostly correct as far as it went. Warming water expands, melting ice sheets add volume, and both effects pile onto every coastline on Earth roughly in step with global sea level rise. That explains a good deal of what's happening in Norfolk and Boston and New York. It does not explain why this particular stretch of coast has been rising faster than the global average, and by a wide enough margin that something else clearly had to be going on. The answer, once researchers went looking, traced straight back to the current we've spent this whole story following. The physics here is worth sitting with, because it runs against the instinct most people carry into this topic. A strong Gulf Stream, hugging the east coast the way it normally does, doesn't just move warm water north. It also, because of the way moving water and the Earth's rotation interact, creates a kind of standing slope in the ocean surface, piling water up on its offshore side and holding sea levels slightly lower along the coast behind it. Picture a fast-flowing river rounding a bend. The water on the outside of the curve rides a touch higher, banked up by the current's own momentum, while the water tucked behind the bend sits calmer and lower. Weaken that current, and the bank collapses inward. The water that used to be held offshore, piled up by the Gulf Stream's own force, redistributes, and some of it comes home to the coast. Research led by oceanographer Jen-Jun Yin and climate scientist Stephen Griffiths, along with work from Old Dominion University's Tal Ezer, has tied specific slowdowns in the Gulf Stream and AMOC directly to specific spikes in coastal sea level along exactly this stretch of American shoreline, including that same 2009 to 2010 weakening event, the rapid buoys caught in the act, the one that came with a documented 128-millimeter sea level jump, about 5 inches, north of New York City in a span of 2 years. This is level 2 again. The moment the data doesn't just look unusual, it reaches into people's basements. This is the part that should genuinely stop you, because it inverts everything the phrase climate change tends to conjure in most people's imagination. A weakening Atlantic current, driven partly by melting Arctic ice thousands of miles away, is helping push seawater up through storm drains in Norfolk on a cloudless Tuesday afternoon. Not a hurricane, not a superstorm, a distant current quietly loosening its grip, and the ocean simply reclaiming a few inches of ground it used to be held back from. Multiply those few inches across decades, layer them on top of already rising global sea levels, and you get a coastline where the flood maps drawn 20 years ago are already, provably, out of date. A slow-motion redrawing of the map that has nothing to do with any single storm, and everything to do with an engine losing torque 3,000 miles out to sea. And if a weakened current can already rearrange the waterline along the world's most economically vital coastline while it's merely limping, the obvious, uncomfortable question is what happens if it doesn't just limp? What happens if it actually stops? For that, we don't have to guess. We have witnesses. They're just frozen, 2 miles down, in the ice of Greenland. Ice doesn't lie, and it doesn't editorialize, which is exactly what makes it such a devastating witness. When snow falls on the Greenland ice sheet, it doesn't vanish. It compresses, year after year, trapping tiny bubbles of the actual atmosphere that existed the day it fell, along with dust, volcanic ash, and chemical signatures that shift depending on how warm or cold, how stormy or calm that particular year happened to be. Drill down through that ice with a hollow steel tube, and you're not taking a sample. You're opening a diary that has been sealed shut for tens of thousands of years. One page, 1 year, sometimes 1 season at a time. The 2 most important entries in that diary, for our purposes, were pulled from cores drilled at sites called GISP-2 and GRIP in central Greenland during major international projects through the 1990s. What they recorded about the Younger Dryas, the abrupt cold snap we touched on earlier, roughly 12,800 years ago, reads less like climate data and more like an emergency broadcast frozen mid-transmission. Layer by layer, year by year, the cores show Greenland's temperature dropping by as much as 10 degrees Celsius, about 18 degrees Fahrenheit, in a window some analyses place at 3 years or less. 3 years to lose 18 degrees. That is not a season getting colder. That is a climate-changing state faster than a single human could finish raising a child from birth to kindergarten. But the Younger Dryas wasn't a one-off freak event, and this is where the ice cores get genuinely eerie. Going back further, through the last ice age, the same Greenland cores reveal a whole rhythm of these abrupt swings. Scientists call them Dansgaard-Oeschger events, named for the researchers who first identified the pattern. And there were at least 25 of them over roughly the last 100,000 years. Each one a sudden jump in Greenland temperature, sometimes by 5 to 10 degrees Celsius within a matter of decades, followed by a slower, more gradual slide back toward cold. Many of these events line up with what are called Heinrich events, periods when massive armadas of icebergs, carved off the ice sheets covering North America and Europe, drifted out into the North Atlantic and essentially dissolved into it, dumping enormous pulses of fresh, cold water directly onto the engine room of the overturning circulation. Fresh water in, sinking stalls, heat transport falters, and the whole hemisphere's climate lurches, all recorded faithfully, layer by layer, in ice that has been sitting patiently underfoot in Greenland for the tens of thousands of years since. The comparison that matters is the one that should genuinely unsettle you more than the temperature swings themselves. Those ancient freshwater pulses came from something dramatic and finite. Enormous ice dams bursting, glacial lakes draining catastrophically, armadas of icebergs breaking loose all at once. It was violent, but it was also, in a strange way, a single, bounded event. The tap turned on hard, then eventually turned back off. What's happening in Greenland today is a different shape of threat entirely. The Greenland ice sheet has been losing mass at a rate now estimated by NASA and the ESA's satellite gravity missions at roughly 200 to 280 gigatons per year on average over the past 2 decades. A gigaton being a billion metric tons, which is a number so large it stops meaning anything until you turn it into something physical. That melt rate is roughly equivalent to the weight of the entire Greenland ice sheet's loss, filling something on the order of 80 million Olympic swimming pools with fresh water every single year, and pouring it directly into the same ocean basin where the ancient meltwater pulses once stalled the entire circulation. It isn't one dramatic burst. It's a tap that was barely open decades ago and keeps being turned, slowly, incrementally harder, with satellite records showing the melt rate itself accelerating across the very years the rapid array has been recording its strange weakening events. The ice cores don't tell us this modern, slow-motion version of the story will end the same way the ancient, violent version did. The scale isn't the same. Not yet. And honest scientists are careful to say so. But the mechanism in that frozen diary is identical to the mechanism running right now beneath the cold blob. Fresh water, arriving in the exact place where salty water is supposed to sink, doing exactly what fresh water has always done to this current, just written this time in a slower hand. Which brings us to the question that every serious researcher in this field is asking themselves, quietly, almost daily now, staring at instrument feeds instead of ice cores. Which specific signals, arriving on which specific dates, would tell us the slow hand is speeding up? Because that's the world we're actually living in right now. Not a countdown to a fixed year, but a live watch with real metrics, real thresholds, and real people checking them. Start with a number the rapid array has been logging at 26.5 degrees north since 2004. The AMOC's transport strength, measured in those spheredrups we described earlier, each one equal to 1 million cubic meters of water moving past that line every second. The multi-year average has hovered somewhere in the range of 17 to 18 spheredrups, with natural swings up and down of several units in any given year. That's the ordinary breathing of the system, the noise scientists expect and don't panic over. What they watch for is a sustained departure from that range that persists for years rather than months. A floor that keeps dropping rather than bouncing back the way it did after the 2009 to 2010 dip. As of the most recent published analyses, the array has not shown a runaway collapse, but it has shown, cumulatively, the long, uneven downward drift that the 2018 Caesar and Thornalley studies flagged as unprecedented in more than 1,000 years, and the four-mooring western boundary study from Miami's Rosenstiel School found that same downward drift independently confirmed at every single latitude they checked. Then there's the freshwater budget itself. How much of that Greenland melt, plus increased Arctic river runoff, plus rainfall changes across the subpolar Atlantic, is actually diluting the salinity of the water that's supposed to sink? Researchers running the OSNAP array in the Erminger and Labrador Seas track this obsessively, because salinity is the second half of the density equation that makes the conveyor turn over in the first place. A steady decline in surface salinity in those specific seas, sustained over multiple years rather than a single anomalous season, is one of the clearest possible warning signs. And it's precisely the kind of measurement that depends on exactly the in-water sensors now being pulled from the Erminger Sea under the recent National Science Foundation funding cuts we discussed earlier. That's not incidental to this story. That's the story. The instrument best positioned to catch an accelerating freshwater signal in real time is the one currently losing its eyes. Beyond direct current measurements, scientists track what are called early warning indicators, the statistical fingerprints of a system losing resilience that Nicholas Boers identified in his 2021 analysis. In practice, that means watching whether the AMOC's variability from year to year is getting noisier, whether the system takes longer to recover from small perturbations, whether the whole thing behaves like a spring that's slowly losing its tension. These are subtle, statistically demanding signals, easy to misread in a short record, and easy to dismiss if you're not looking for them across decades rather than seasons. But they were exactly the kind of signal Bors found already present in the 20th century record. Evidence, in his words, that stability may already have been eroding before most of us had ever heard the word AMOC at all. And then there's the blunt, brutally simple metric underlying all of it: Greenland's annual mass balance, tracked by NASA's GRACE and GRACE follow-on satellite missions, which weigh the ice sheet from orbit by measuring tiny fluctuations in Earth's gravity field. Every year that number comes in more negative than the last is another data point feeding the freshwater tap that ancient Heinrich events once opened violently and catastrophically, and that the modern climate is now opening slowly, continuously, without any single dramatic headline attached to any single year. None of these thresholds, taken individually, gives anyone a date. That's worth restating plainly, because it would be irresponsible to pretend otherwise. The IPCC's sixth assessment maintains high confidence that an abrupt AMOC collapse is very unlikely within this century, while stating openly that confidence in longer-range projections beyond 2100 remains low, precisely because the tipping point behavior this system may exhibit isn't yet something models capture reliably. What's changed isn't the certainty of a collapse. What's changed is the shrinking gap between what serious, credentialed, careful scientists once considered a remote, centuries-away hypothetical, and what they now discuss as a plausible risk within frameworks that matter to policy, insurance, and infrastructure planning happening today. The official position, from NOAA to the IPCC to the Potsdam Institute, remains one of vigilance rather than alarm. The ice is not confirmed thin at any specific step ahead of us, but nobody credible is willing to promise it's solid all the way across either. That's not evasion. That's what honest science sounds like when it's genuinely at the edge of what current instruments can tell it. So we're left standing, at the end of this investigation, roughly where we started, beside the ocean, listening. Except now we know a great deal more about what we're listening for. And there is something almost fitting about that. Because if this story has one true center of gravity, it isn't a model, or a headline, or a single alarming study. It's the ocean itself, and the fact that it keeps the score whether or not we're paying attention. Every mechanism we've walked through in this story, the sinking water in the engine room off Greenland, the cold blob spreading south of Iceland like a bruise the planet can't explain away, the buoys strung across the Atlantic on their railroad wheels, quietly logging spheredrups since 2004, the ice cores 2 miles down holding a frozen record of exactly what happens when this system fails completely. All of it is really the same story, told at different timescales. The ocean does not forget. It does not round numbers in its own favor. It does not care whether a given year's melt was politically convenient, or whether a monitoring budget got cut in the middle of the most important decade of readings in the array's history. It simply accumulates every gigaton of fresh water, every fraction of a degree of warming, every spheredrup of weakened transport, and it carries the total forward, indifferent to whether anyone downstream is prepared for the bill. Wallace Broecker, the same geochemist who gave us that conveyor belt diagram back in 1987, spent much of his later career trying to make one-point land with policymakers who kept treating climate as something smooth and gradual. That the climate system, he said, is an angry beast, and we are poking it with sticks. He wasn't being poetic for effect. He'd spent a career staring at ice cores that recorded exactly how badly that beast has reacted before, in swings of 10 degrees Celsius inside 3 years, in a hemisphere thrown from thaw back into ice age conditions for over a millennium. What we've done in the decades since Broecker drew that diagram is build the instruments to actually watch the beast breathing in real time. And what those instruments have shown us, again and again, from the winter of 2009 to the cold blob spreading beneath our satellites today, is that the beast is stirring in ways our models didn't expect, at a pace they didn't predict, in a century we are all going to live through. We don't get to know the exact date. Nobody honest will hand you one, and anyone who does is selling you more certainty than the physics currently allows.
What we do get, right now, is the fog itself.
And the choice of whether to keep walking across it blind, or to keep the instruments running. Keep the buoys in the water. Keep the cores coming up out of the ice, and let the ocean keep telling us, 1 sverdrup, 1 gigaton, 1 degree at a time, exactly how close the ice underfoot has actually become. The water is colder than it should be south of Greenland. The current is weaker than the models promised. And the ocean, patient and exact and utterly indifferent to our deadlines, is still keeping the score.